Interpreting a confidence interval. So if you could actually take every sample of size n from a given population and then compute the corresponding point estimate and C% confidence interval for the parameter from each of those sets of sample data, you would find that C% of those intervals actually contain the true value of the parameter, which means the rest of them, so 100 minus C% of the intervals, would not. So for example, if we compute a 95% confidence interval, that means if we could actually take every possible sample of size n, 95% of them would give us an interval that actually catches mu, and means the other 5% of the intervals would not. Unfortunately, we do not get to take every sample of size n from a given population. If we could do that, then obviously we could just sample the entire population and not have to look at statistics. We would just actually know those parameter values. So we usually are only going to get one sample, which then will just yield, one point estimate, one value of p hat or one value of x bar. And from there, we're going to be able to create just one interval estimate. So we'll never know if the interval we computed actually contains the true value of the parameter or not. So again, this idea back to inferential statistics, they're educated guesses, which at the end of the day means they're still guesses. So all we can say is that we are C% confident, so like 95% or 98% confident that it does. So be careful here. We are no longer dealing with probabilities, so we're not using the word chance or probability with a given confidence interval. So these are words that we use when we are talking about random variables. So we use those words when we were talking about intervals of x bar or p hat back at the end of chapter 6, because these values vary from one sample to another. In this section, we are talking about the population parameters. So things like mu and p. Okay. These are not random variables, so it doesn't make sense to use the words probability and chance. These values are some fixed value. We just don't know what that fixed value is. So when we're talking about random variables like x bar and p hat, we use probability notation and we talk about probabilities. Now we're looking at estimating population parameters like mu, and I don't know why I wrote a sigma there, p. We're going to use the word confidence. All right, so let's take a look at example 8.1.1, where we're going to state the statistical interpretation of a confidence interval. So suppose you have a 95% confidence interval for the mean age a woman gets married back in 2013, which is when this data was looked at. And we get this interval that runs from 26 to 28. So this is not an ordered pair, this is interval notation. So state the statistical interpretation of this statement. Okay, so I'm going to write up here just with symbols, and then we'll put it into the actual language and context of the problem. But we are 95% confident that mu is in this interval. Now, the wording that we've been learning for mu, since it stands for the population mean, is the mean measurement, whatever variable we're looking at, of all objects. So in this case, we're going to be looking at the mean age of all women got married back in 2013. So as we write this out, and again, we're dealing with parameters, so we're going to be using this word confidence and not probability or chance. So we are 95% confident that the mean, if we call it like marital age or age you get married, of all women in 2013 was between 26 and 28 years of age. Now, if we could actually have gone back into 2013 and actually talked to every single woman and computed the mean age that they got married, okay, we don't, again, we are 95% confident that that mean would end up being between 26 and 28. But that also means, again, that we're 5% confident that it would not be in that interval. Again, when we're doing inferences, at the end of the day, again, we're just making educated guesses. So as long as we're looking at sample data, we'll never be able to say that we're 100% confident in what we're saying about the population. All right, so suppose a 99% confidence interval for the proportion of Americans who have tried marijuana as of 2013 is between 0.35 and 0.41. And again, we want the statistical interpretation of this. So again, I'm just going to write underneath it here before we look at the context. What this is saying is that we're 99% confident that P is in this interval. And so if we put in, again, and so from practice and writing in the last couple chapters, for P we're going to have the proportion or percentage of all objects that are in some category of interest. So in this case our objects are going to be Americans, and the categories of interest is going to be that they have tried marijuana. So as we write this out in context here, we're going to say we are 99% confident that the proportion of all Americans who have tried marijuana and we'll throw in the year here to be more technical. So as of 2013 is between 0.35 and 0.41. Now we could also, instead of proportion, we could use the word percentage and then change these to 35% and 41%. It's an equivalent statement. All right, so one last thing to know about confidence is how the sample size and the confidence level affect how wide the interval is. And so the following figure demonstrates what happens to the width of the interval as you get more confident. Okay, so this shouldn't be so surprising that if we want to be more confident that our interval actually catches the true value of the parameter, that it would take a wider interval to do that. Okay, so the higher level of confidence makes the interval wider. Okay, which means that the margin of error is larger. That give and take from the center. So there's a trade-off between width and confidence level. So you can be really super confident about your answers, but your answers will not be very precise. So like I could say, I'm 100% confident, that the temperature outside today is going to be somewhere between, negative 50 degrees and 100 degrees. Okay, and I'm probably going to be right with that statement, but it's not very useful. Okay, so, or you can have a precise answer, okay, where you can get your interval down to much smaller with a small margin of error, but then you're not going to be as confident about the parameter being in that particular interval. All right, so the other thing to look at is how sample size affects the size of the interval. So the figure below represents confidence intervals calculated on a 95% interval, and then we just kept taking larger samples, and we can see that that makes the width of the interval narrower. And so that should also make sense, since larger samples are closer to the true population, so our point estimate tends to be closer to the true value. Okay, and if we think about those standard deviation computations, they had an n in the denominator. So as n got bigger, that standard deviation value got smaller. So we can see that here, with the sample of size 30, we're 95% confident some parameter is in this red interval. But had we instead looked at 100 data points, we could have shrunk it to this blue interval. Or had we talked to 1,000 people, we could have made it this, tinier kind of bluish purplish interval. So as we increase the sample size, so as we increase the sample size here, we're going to decrease that margin of error.